My name is Piotr Skowron, and in this talk, I'm going to consider a model where there is a group of candidates and a group of individuals who have preferences over those candidates, and our goal is to select a fixed size subset of the candidates. The main question of this talk will be how to fairly, in this context, proportionally select a subset of candidates. Here in the left-hand side picture of in this slide, we can see that we have 5 voters. We are given a set of candidates, and the voters, we assume in this talk that the voters express their preferences by approving the candidates. For instance, voter V1 approves the green lady, the red guy, the orange guy, and the pink lady. And the voting rule is an algorithm that takes as input such a preference profile with approval-based preferences, and a committee and the size of the committee to be elected, K, and returns a size K subset of the candidates. So, how to make such a choice in a proportional manner? How to define proportionality? Sometimes, when the preferences of the voters are very well structured, proportionality can be defined very intuitively. However, sometimes in many contexts, these preferences are not so well structured. So, for instance, let's look at these preferences depicted in this picture. Which committee would be proportional here? It is not easy to point out such a committee. It is not easy, and not to mention defining formally what proportionality means. This question has been addressed in the literature, and a number of concepts for formalizing the proportionality have been proposed. Now let's look at 3 such concepts that appear in the literature. These concepts are based on the following intuitive idea. Let's look at this group of voters, V3 and V4. So we can see that this group of voters form 1/4 of the society. So in a way, they should have right to decide about 1/4 of the committee, that is about one candidate. They all agree on one candidate. So in some sense, it is possible to satisfy them by choosing a single candidate. So our intuition is that such a group should not be neglected by our rule. The axiom of extended justified representation would say that at least one of these voters from this group should have at least one representative in the elected committee, a representative that is a candidate that she approves of. There are also 2 weaker axioms, proportional justified representation and justified representation. However, for this group of size n over k, these axioms are equivalent. However, if we look at group of size 2 times n over k, then those axioms have a slightly different meaning. And we can see here, for instance, if we look at this group consisting of the voters V1, V2, V6, V8, we see that this group forms half of the society. Thus, it should be able intuitively to decide about half members of the committee. Those voters agree on that some 2 candidates are good, are acceptable to those voters. So in some sense, these groups, it is possible to satisfy this group in a way by choosing 2 candidates. Here, the axiom of extended justified representation would say that at least one of these voters should have at least 2 representatives in the elected committee. Proportional justified representation would say that these voters should approve at least 2 different committee members. And the axiom of justified representation says that in this case it says nothing, because justified representation is a variant of extended justified representation, but only applied to groups of specific size, namely of size n over k. Okay, so formally, extended justified representation says something like that. If there is a group with at least L times N over K voters, so once again, N is the number of voters, K is the number of candidates that we would like to select. Thus, in a way, intuitively, N over K is the number of voters who should be eligible to decide about a single candidate. So if we have a group of L times N over K voters who approve at least L same candidates, then extended justified representation requires that there should exist a voter who approves at least L members of the elected committee. In our work, so this is the definition which is already well studied in the literature, but in this work we defined a slightly different notion. So now, instead of requiring that at least L members of elected committee should be approved by this single voter, instead of putting here a hard constant, we will put here a function, and this function, in some sense, is a quantitative variant of the axiom. So, for instance, we can say that if f is a function which is which takes high values, then the rule will be proportional. We'll have good proportional guarantees. However, if this function takes only low values, then this means that the rule would behave not very proportionally. So another intuition would be that this function f specifies the shape of proportionality guaranteed by a given rule. And the second change that we make in this definition of EGR is that we now do not look at one voter from a group, but we rather look at the average satisfaction of the voters within this group. That is, we measure the average number of committee members who are approved by the voters in the given rule. And this function f is called proportionality degree. So here is the hierarchy of our axioms known in the literature. EGR is stronger than PGR, and PGR is stronger than JR. Those axioms imply each other. However, this hierarchy is not very accurate and does not allow to well reason about proportionality of committee voting rules. The first reason why this hierarchy is inaccurate is that there is a huge gap between the strength of these axioms. So EGR is a very strong axiom. PGR is much less expressive and is much weaker axiom, and JR is even weaker than PGR. On the other hand, this hierarchy might be inaccurate because JR might not be satisfied by a rule only because small groups of voters are slightly underrepresented. So these kind of inaccuracies are fixed by our axiom of proportionality degree because it really allows to measure, to quantify the level of proportionality, and in some sense to very well and very precisely describe how this proportionality looks like, and to capture the whole spectrum of different types of proportionality, of different strengths of proportionality. So in our work, we also look at we mainly focus on two prominent committee election rules, which have been proposed by these two mathematicians in the late 19th century. So the first rule that we'll look at is proportional approval voting, and this rule is defined as follows. We check every possible committee of size k, compute the score of such a committee, then we pick the committee with the highest score. The score of a committee is the sum of the scores that this committee is assigned by voters And the tricky part is how to define a score that is assigned by a voter to a committee. According to PAV, we take the following formulation. Assume that a voter approves T members of the elected committee. Then this voter assigns to this committee the following value: 1 plus 1/2 plus 1/3, and so on, plus 1 over T. For instance, let's look at this example, and let's look at this committee that consists of 3 candidates: the green lady, the red guy, and the blue guy. Here you can see that voter V1 approves 2 members of this committee, that is the green lady and the red guy. So this voter assigns the score of 1 plus 1/2 to this committee. Voter V2 similarly assigns the score of 1 plus 1/2 to this committee. And finally, we sum up all these scores, and this is the final score of the committee. And the rule picks the committee with the highest score. We can also define a sequential variant of this proportional approval voting. This sequential variant is defined as follows. We start with an empty committee, and in each step, we add to this committee 1 candidate, namely the one that would increase the PAV score, defined as before, using these harmonic values, most. Sequential proportional approval voting has one advantage over proportional approval voting, that is, it is computable in polynomial time. However, it is not clear how proportionality of these 2 rules compare. Another rule that we will look at is the Fragments Rule. It is defined slightly differently. Here we assume that voters earn money with the constant speed, say $1 per time unit, and we assume that if at any point in time there is a group of voters S who all have N dollars in total and who all approve a not yet selected candidate C, then what we do is the rule requires that those voters are forced to buy this candidate C. That is, what we do is we add C, this candidate, to the committee and make all voters from S pay for C. That is, we reset their budget to 0. So in a way, this means that buying a candidate costs N dollars, and we buy those candidates somehow greedily. When the voters earn enough money to afford for a candidate, then they always do that. So the main result that we present in this paper is the theoretical estimation of proportionality degree of different rules. So actually, one such result is already known in the literature, follows from the work published in AAAI in 2018, and it says that PAV, the proportionality degree of PAV, is L-1. And further, it can be shown that no higher proportionality degree can be achieved by any rule. So basically, L-1 is also an upper bound on the proportionality degree of any committee election rule. So in some sense, PAV is optimal according to to the measure of proportionality degree. However, in this work, by more complex proof, we also have shown that the proportionality degree of the Fragments Rule is L-1 divided by 2. So in some sense, this result can be interpreted that the guarantee offered to groups with cohesive preferences by Fragments Rule is twice worse than the guarantee given by PAV. It is interesting because now we can understand what is the degree of this proportionality, and what is in some sense, we can quantify the difference between different rules. Our technique for proving proportionality degree of sequential variant of PAV is quite different. So here what we did is we found an algorithm that, given a committee size K, computes proportionality degree of sequential PAV for committees of size at most k. So it is important to understand that here this algorithm basically does not do any kind of experiments, but it computes a hard analytical guarantee. Sometimes we can also argue that maybe this result is more fine-grained and even more interesting than having just a proportionality degree that works for any k, because usually when we elect a committee, we know the size of the committee to be elected in advance, and then we can measure what is the proportionality degree of this rule for the intended committee size, and we can make a more precise estimation and more precise the decision and a better decision which rule should be used in this context and for this value of the parameter key k. And these are examples of outputs of our algorithm for different committee sizes k. And we can see that for moderate and reasonable values of the committee size k, for the committee size, the guarantee of sequential PAV is better than the guarantee offered by the Fragments Rule, which is interesting. Okay, so in this talk, what we did, we quantified, we presented a new measure of proportionality, which is quantitative, which allows not only to say whether a rule is proportional or not, but to precisely estimate how proportional is a given voting rule. And this definition, this quantitative definition, allowed us to clarify some misunderstandings that appear in the literature. So one such a misunderstanding is that based on the so far known results, one could say that sequential PAV is not a proportional rule. This is because it does not satisfy JR, a very weak axiom. On the other hand, our result says that this is not the case, that sequential PAV has a very good proportionality degree, and the reason why it does not satisfy JR is that it only slightly underrepresents very small minorities of the voters. The second misunderstanding was that max fragments, which is a different variant of the fragment rule, that it is a proportional rule and in particular much better than sequential PAV. So for instance, max fragments rule satisfies the axiom of PGR, which is stronger than JR. However, this conclusion is also not very correct, because our results say that max fragment has a very bad proportionality degree.